Let's explore Newton's law of cooling in Desmos. Newton's law of cooling explains a change of heat of an object with exponential decay. So an example would be you have this hot cup of coffee or something like that that's just set on a counter in room temperature, and that temperature is going to asymptotically approach the temperature of the room, following pretty closely with exponential decay. This law does have its limitations. We don't really want to use it for big temperature changes, and we should be mindful of changes in states like going from a gas to a solid, or gas to a liquid, liquid to solid, melting, boiling, things like that. But it is a great way to explore applications of exponential functions in a way that really makes sense with what we understand based on our experiences. And I'll add that Newton's law of cooling can also be used for warming. So if you have a cold item, it could asymptotically approach room temperature from either above or below. It's a decay function sort of either way. It's just that we have a vertical flip depending on if our temperature is above or below the temperature of the room. I've created this graph and shared it with you in the video description. There's also a companion document you can open to find the inputs, so you can copy and paste these into other software, or check out the transcript if that's helpful to you. And what I'm going to do in this video first is just explain how I created this. That will involve talking a little bit about the algebra that goes into finding that constant rate that we see here with k. But then we'll add some features so I can show you some things that Desmos can do that you may or may not be aware of. And lastly, we'll go all the way back to the beginning and try it with different values and see how that changes things, see if there's anything we need to watch out for. That way you can use this graph or create a graph of your own to solve problems or create visual graphs of problems that you're working on. This is really great if you're writing a report for a science class or something like that. Even if it has nothing to do with Newton's law of cooling, you might learn something that applies to your function or your graph that you're creating. All right, let's dive right in. So right at the beginning, I'll just let you know I've arranged everything in a folder. We don't see the graph over here yet. That's okay. We're kind of locked into this default viewpoint, which scales things equally. Now our temperature is starting at 205, so that's way up that y-axis. But first, let's just go through the function, and then I'll show you how we can visualize it better. I'm just using some text notes to label things. We've got an initial temperature T sub 0, and that does give you a slider for that, so you can adjust that if you want. You can also type in whatever temperature you're starting with at time 0. Same with the surrounding temperature. And then we have the generalized function. A lot of times in algebra text, we'll see a capital A coefficient, which we could really align to transformations, thinking that as a stretch factor. But I like to use all of these contextual variables so that we can really understand how they're all going into there. And it also takes a step out of the process of finding that A value with some algebra. With our scenario, our initial temperature is higher than the surrounding temperature, so our E coefficient will be positive, and K, I'll just let you know, is going to be this negative rate. So what we'll have is a decay function that approaches that surrounding temperature. That's going to be a horizontal asymptote. If we're thinking of transformations, we can think of that as a vertical shift, shifting the whole graph up from that x-axis. And with the coefficient being positive and k being down here, we can peak a negative value, we will decay down. Now, if our initial temperature was below the surrounding temperatures, so for example, this is room temp for Fahrenheit, roughly 67 degrees Fahrenheit. Let's say our initial temperature of the object, maybe it's colder, maybe it's only 40 degrees, then 40 minus 67 will give us a negative coefficient. Think of a negative coefficient as a vertical flip, so that decay function is now looking like it's upside down, or it's increasing and asymptotically approaching that horizontal asymptote. So that covers the concept of transformations a little bit. We do have this inputted factor here. Now that K factor is going to be sort of our rate of heat transfer. It could depend on a lot of things. For example, if we have a bowl of soup that's hot versus maybe some hot concrete or something like that, these will maybe have different rates of heat exchange, and it's thermal conductivity and a lot of other factors. If you've taken physics, think of it like that coefficient of friction. When you have sandpaper, it's rougher, it's going to be a more force that's applied versus ice that's smooth. Same thing here. It would be really hard to theoretically calculate this. We have to do it based on the empirical evidence that we see, which is really just an initial point and a start and a first timestamp. So we let some time pass, we see how much the temperature's dropped, and then we just continue drawing that line from there. Algebraically speaking, what it is we need 2 points to plug in, so that way we've got enough information to solve for the K value. Anytime you use Newton's law of cooling, if they didn't give you K, you typically are going to have to find that. So there is a complicated looking formula down below where I found that K. Let me show you how that takes place. I'm not one to really love writing things down on paper. I do recommend grabbing a paper and a pen and following along if that works for you, but you might be able to visualize these steps just like I do. Now let's imagine this relationship at a point where the time is T1 and the temperature is capital T1. So the capital T1 ends up on the left over here, and the time T1 is up in the exponent. Well, I could even copy and paste this and show you what this process looks like with our actual inputs. So there's my T1 temperature. There's my little t subscript 1 for time. Now imagine solving for K step by step. The first step would be subtract Ts from each side. That's that surrounding temperature. Sometimes I call that surface temperature just accidentally. Now, if we're solving for K, we have to isolate the exponential or divide by its coefficient. So here I will divide each side by that difference in temperature from the initial to the surroundings. And we see something that does look familiar from down below right here. Now, lastly, we need to get this K by itself. We need to get it out of the exponent. Anytime we want to get a variable out of an exponent, we need an inverse exponential. That's our log. Or in this case, with the base of e, we would think of it as applying a natural log to each side. We can use one-to-one property to do that. Or we would want to use the definition of a natural log, which kind of maybe looks a little different. I like to just think of it as, let's just apply a natural log function on each side. That's an inverse exponential. It will either cancel this e, or you could say it brings the exponential out as a coefficient. And it doesn't really want to paste it as a coefficient. Let's see, kt underscore 1. So there is that coefficient. And natural log of e is asking us what power of e equals e. That'd be e to the 1. So that one just sort of appears to vanish. And the very last step is divide each side by t sub 1 or multiply by 1 over t. And there's our k value. Now, going through this solving process, if we're going to do it again and again and again for different numbers, why not just do it what we call implicitly with variables and then plug in our variables? So if you're doing the homework, you want to make sure that that's okay for your instructor. But I always recommend just solve it with variables and write a little note on the side, put it in a box. This is how I find K, and now I can do this on every single problem much quicker than having to go through the algebraic steps again and again. Now, as are with the other variables, this T1, lowercase and uppercase, this is time for our first timestamp and temperature at our first timestamp. Feel free to change those depending on the problem. Here I'm essentially saying after 30 minutes, the temperature dropped from 205 to 160. Now with all of those features explained, let's actually look at this graph and start to connect the dots. What I would want to do to best frame this is either adjust my graph settings. You can start by potentially just zooming way out, and then I'm using my scroll wheel, just kind of find the spot that looks good. But you may find that it's difficult to frame it exactly how you want it, especially if it's a really slow decay, or maybe you get X looking good but Y is not looking good. So what I like to do is add a table, and the way I'm going to do this is add all my components in a new folder and call these added features. So if you follow along, you can arrange it however you want, but this will help you separate what I'm adding from what was already there. One of the features we can add is a table. This usually defaults to X1, Y1. I think I maybe already did that and didn't start with a new graph, so it's going to the second subscript. But I'm actually going to change it and use the variables that I'm already using. That would be a lowercase t, and then I defined a function with an uppercase t, so I'll just use that function notation. So instead of inputting points, I'm actually inputting t values, and it will evaluate the temperature. So after 0 minutes, it's at 205. You can see it added a point up there. And I'll just go down a row and go 30 minutes, and it's evaluating it. It's getting 160. And that value should be really tied to what I have here. And I could actually see that changing in real time if the temperature is dropping very quick or if it's dropping slower. I might put an upper bound of 200 on that, so it will let me to slide that. Let's see, here we go. Now it will let me slide that up higher. So that would be a very slow temperature drop. But let's go back to, I'm going to undo and go back to what it was, which was 160. Now, this is something that I love about Desmos, and sometimes you'll see this in other spreadsheet apps as well. Once I have 2 points in that first column, you see where my cursor is, I'm just going to hit enter, and it's going to continue that pattern. This will not work. Sometimes if you have a blank space, let's see, I've noticed, see here, if I have a couple of blank rows, for some reason, just hitting enter for 30 doesn't work. But if I delete them, now it's working fine. And it will just continue adding the pattern. You can see it's plotting the points as we go. Let's go up to 300 minutes. I think that's a good range of values to showcase. And here's the beauty of adding that table. Right down here in the bottom left of that input is a zoom fit, and it will adjust our axes separately to frame that as best as possible. It didn't do a whole lot in this case. We'll come back through and look at a slightly different set of numbers, and we might see a more dramatic effect there. And just remember, you can always go fine tune these in that graph settings. You can also add labels like T for time in minutes, and capital T for the y-axis is temp in Fahrenheit. Just kind of abbreviate that so it's not taking up quite so much space. And that's all looking good. I may not want all these points here. You can toggle those on and off there. One other thing that you're seeing here is a regression option. That would be if we have empirical data and we want to model it, if it's an imperfect fit, or even if it's a perfect fit, it will use regression and that concept of least squares regression or different methods like that to sort of construct an equation or a relationship for these points. That's something I do plan to cover in a video later, but for now I don't have a great video on that topic. Now the next couple features that I'll add, they might seem kind of basic, but just things like a horizontal asymptote. Here we've got a surrounding temperature of 67. Let's plot that as a y value. And we see, even though we're using a temperature scale, it's still going to be better to use y than t, because it really would want to see that capital T as a variable, whereas y is more of a plot command that you're giving it. So we plot it as y equals 67. We can edit that color, make it blue, make it dashed. I like to make it a little bit fainter, so I'll drop the thickness a little bit, and that looks really nice to show us that horizontal asymptote. If you wanted to label that, there's no way to label a line, but you could add a point. Let's say we just put this point at 0 and t of 0. Oh, actually, let's do it at 0 t s. There we go. So there's a point there, and I can label it the surrounding temp. And that's a good way to label it. You see that it did something else. It made this a movable point. Actually, because I used my variable that's defined, it's using the slidability of it. I did make a slight error here, and that's back with my horizontal line. Maybe not an error, but I could just use the TS and make sure that those are sort of locked together. It's a nice example of using the dynamic effects and sliders in here. I want to go back to 67, so we're keeping that constant. Now the other thing I might do is turn that off. If I don't want it to be movable, that could really screw things up. You can edit that list and remove the dragability and even remove the point itself. Put that label where you want it. And then now it's fixed in place for this specific set of parameters. All right, and other things I can add are points marking other spots along the line. So for example, 0 and T of 0 will be my initial temperature. And I could also put in my T subscript 1, T1, and then capital T evaluated at that point. This was my first timestamp. And you'll see sometimes that these come in as movable points. And that's just because I'm using these variables that I've defined above. So we could change that as well. I'm going to undo and just keep it where it is and get rid of that slidability as well as the point itself. Well, maybe I should leave the point, to show where that is. But I think it can be good to make these all matching. All right, so that's a couple points that I'm adding to add some depth to that graph. You might notice that this graph goes back into the negative space. And that's something that we can fix using a restriction on the function. Restrictions, you have to go all the way to the right end of it and add braces. Typically, I just restrict the input. So t would be greater than or equal to 0 for that. And it's just going to plot to the right on that positive t axis. With some functions, you can actually restrict y. I found it hard to do it probably because of the variable setup here. Although if you know the bounds for y using the function inputs, that would work as well. So essentially just plug in f of something where you want it to m. I think to me that would apply maybe to what I said is a change of state. So if it goes from a gas to a solid, I might want to stop right there. So I would want to stay between 32 and 212 degrees for a liquid, for example. Now, I did add that feature to the original function. There's not really an easy way where I can do that in a separate place. The last feature I want to add is a solution. So let's say you've got a question that asks you how long or at what time is it going to reach, let's say 100 degrees. We can see that right there. You might be able to find it by dragging. So if I drag my cursor, there's 100. You can actually really snap to that spot very easily just by typing x equals 100 and clicking on the point, and it will even export it to the list. So it looks like, oh, I should do y equals 100. That was a grave mistake because I want the temperature to be 100 and I want to figure out the time. It was very close to actually 100 minutes, 100 degrees, but it looks like after 108, almost 109 minutes, we've dropped to 100 degrees. And there's that solution there. But there's an even better way. I'm going to delete both of those. Let's just solve for little t. What I'm going to do is actually define an inverse function. This gets into the concepts of logs again. I will call it little t. We can call it t sub s for a solution, for example. And the input will be a capital T. Defining a function says I need something on the other side of the equals. I need that. And it's actually going to be very similar to the k value here. Because if you remember, we solved for k by isolating the exponential, then doing a natural log, and the very final step was dividing by the little t. Specifically, t1 was what we have. So instead of dividing by t, we'll just divide by k. So all I'm going to do is copy this. Oh, and I guess you could really see it may be easier. Just multiply each side of this by t1 and divide the k back over, and you got the same thing. So way down here, my inverse function, it will have a 1 over k in front. And the other piece that's changed now is this t1 was really specifically for that first timestamp. That was the temperature that we were getting after a specific amount of time. We want that to be the input variable. So we have a bunch of constants: initial temp, surrounding temp, the constant of heat transfer, but we'll be inputting a temperature, and that's in that one specific spot. Now, it might be easier to really imagine this if you go all the way back to the original function and solve it for little t there, because then you will actually have your capital T coming from that left side. You just kind of have to remember we changed it to t1 for our specific first timestamp. Now we got to change it back to a variable t. Sometimes all these subscripts can get confusing. I totally can relate to that if you're dealing with that. That's why sometimes we use that H, K, A, B and try to have all these different meanings. Now if I set this back to my default zoom and then just start to zoom out, we'll see a symmetry with respect to the identity y equals x. So we've got that symmetry that we usually expect. Where they cross should be when the time and temperature is the same. So after 102.7 minutes, we're at 102.7 degrees. So all those get into that concept of inverses. Now, I think plotting this may be a distraction. I think it really won't help us that much in visualizing it, but what we could do is just use it to plot points. So for example, let's say we want to find how much time it takes to get to 100 degrees. We would do T solution, T sub S is what I called it, 100 degrees. It takes 108.76 minutes approximately. Well, then I could plot that. And for an approximate value, I could put in an X, or a lowercase t, I should say, of 108.76. Or I could recognize the fact that right here is a precise value. Let's just paste that in. This is a precise amount of time to reach 100 degrees. And there's that point there. So this is an interesting view of inputting a point using an inverse function. Usually we input x and get y. Think of x and y as our time and temp here. So we did that multiple times above, where I inputted 0, I inputted t1. But now we're going to input a y value into an inverse to get the x value. I love this stuff. It's a great way to really deepen your understanding of inverse functions and how they work. The input becomes the output. The function moves from the y slot to the x slot. And it all works great. We've got really precise values there. More precision than if we just click at a point on the line and see what we get. So that's a tool that you can add. You can definitely use this in all kinds of different ways. Some people will create a slider. So we could create an unknown temperature. Let's call this, we already did T sub S. So I'm going to have to do T sub U for unknown T. And I can now convert my point here based on that T, capital T sub U. And now that is a slider. TU, let's put it in this range that we'd actually get. I'll start with 190, for example. Aha, now I have a slidable point that's based on an inputted temperature, and it gives me that outputted amount of time. So that's using some solving, using inverse functions to add a lot of value and usability to this graph. Now I'm going to go all the way back to the beginning. Let's say that instead of maybe a hot cup of tea, we've got a frozen steak at 0 degrees Fahrenheit. Something broke along the way because our graph completely disappeared. So I'm kind of wondering about that. Let's go through and see how all these look. Well, I think maybe this initial timestamp isn't going to make sense anymore, because if we're starting at 0 and approaching 67, we need to have a temperature in that range. So let's say we start at 0, we go up 25 degrees in 30 minutes. Now it's all automatic. There it is. We've got a great graph. We've got that exponential decay that's flipped. The only thing that maybe isn't great here is the scaling. And since we already made that table, look, all of our values have updated automatically. After 60 minutes, we're at almost 41 degrees. And we could see, for example, how long does it take to get to the freezing point? But what I would do with this is use that zoom again. Looks like I have to turn those points on, and now my zoom option comes up, zoom to fit, and that to me looks a lot better than the scaling before. So it's a really quick way to scale it, at least get you in the ballpark of where you want to be without having to guess what you want to use for your axes cutoffs. Now I will say here, there's a limitation. We are going past a melting point. So this is a frozen steak at 0 Fahrenheit. And after, let's see, about 41, 42 minutes, we're getting to 32 degrees. So we might add that limitation. That was at the very end of the function where we restricted time, but we don't really know how high to go. So it would be from 0, I'm going to reverse the order here, to some value. Now I'm going to just use my solution down below to find that. So the solution function is here. Let's look for 32 degrees. That's going to be our melting point in this case. And now we've got an outputted value here. The order kind of seems a little bit off there. It will definitely look below for inputs if it doesn't find them. But you could call this a melting point temperature. So time to melt, I'll do T_M to label that. And now I've got a variable that I can use, T_M, way up above. And let's just cut this off at that melting time. So at that point, we may not follow that same curve. It may take an extra minute to melt where it doesn't necessarily change temperature too much, and then it will kind of resume its path. It'd be really interesting to have more theory on that. And a lot of problems may disregard that completely if you're looking at a homework problem, for example, where we try to simplify things as much as possible. Now, I hope that this helped you out. If there's anything else you'd like to see, please leave a comment. I'm always making new videos, and I'm remaking videos too. So at some point down the line, I might come back to this. If there's something you'd like to see covered, let me know, and subscribe so you can catch it when I create that video.